Okay, in this video we're going to talk about spontaneity, and I'm just going to clean up a little bit. We lost a little bit of quality on our last video about spontaneity, so I'm just going to clean this one up, and we're going to go at it again. So with this, with determining spontaneity, what we want to be looking for is looking at our reduction potential chart. I've got one here, and I've also got one on the previous page, and we want to look and make sure that the reduction potential of the two elements being reduced and oxidized are complementary. So what I mean by this is we're going to first identify which one is being reduced. So the reduced one will always be the positive one. So it would be the copper here, or the sodium, or the silver, or the iron, or the other iron here. All of these have positive charges, so that indicates that they are ready to be reduced. And then we go and we find the reduction potentials for those elements. So let's look at copper 2+. Copper 2+ is on this chart. Let's see, I see one copper 2+ here at 0.34. That's the one I want to use. We had a question in class about what about copper +1 going to copper, or copper 2+ going to copper +1, which we can also see right here at 0.16. Well, we want to always choose the larger one, because the larger one means the more spontaneous one, the one that's more likely to happen. So in this case, we can just make a little recording here. We're going to write the reduction, the element that's being reduced. That one should be written as it's presented on the board. So this is 0.34 volts. That is our redox potential. Now the other element is going to be the oxidized one. So I'm going to look for some tin over here, and I believe that tin might not be on this one. So we're going to scroll up. Oh, I do have I did use tin earlier. So we'll see on the previous page here that if we go up to tin, we can see the reduction of tin, right? This is reduction in this direction, is negative 0.14. Well, I'm not interested in the reduction. I have not been given tin ions in this case. I've been given tin metal. So tin metal is going to be oxidized. So that means it's going to go in this direction. So whereas this number was the redox, this is our redox number, our reduction number, I want the oxidation number. Well, this is luckily very easy to find. It is simply inverting the sign, 0.14, positive now. So I'm going to go down here again. So now that we're talking about an oxidation potential, I'm going to put 0.14 volts, and I'm going to add those together to see if there is a positive value here. So what happens when I add those together? I get a total of 0.48 volts. That's a positive value. Great. It's positive. It's spontaneous. So if the E sum of E maybe, or the E of the cell, we'll just call it cell. That's what we'll use when we do a voltaic cell. If the E cell is positive, the reaction is spontaneous. Okay, so let's look at one that might not work. So we should complete this reaction. So to complete it, we have to put the balance in. Get rid of that. So to complete the balance, we're going to have a copper metal here coming out of the solution, and we're going to have tin 2+ in this case going into solution. So taking a little bit of copper nitrate and some tin metal, and you could probably put some metal shavings in, for example, or even a strip of metal. Stick those in a solution together, and you will find that copper metal is going to start to deposit in the solution somewhere, probably on top of the metal, as that's where the electrons are being made. Similar to the silver tree that we've seen in class. All right, so let's look at the next one. This is zinc solid and sodium as an ion. So looking at the one with electrons, the zinc here. So zinc's got electrons, but the sodium does not. So I'm going to look for the sodium actually. Here's sodium, and this is my value. So sodium is negative 2.71, and that is our reduction. That's our E red. So now I need an E ox if this is going to be a redox reaction for zinc. So I'm going to look around for a zinc here. Oh, here's zinc right there. And right now the reduction, right, this is E redox, is negative 0.76. So my ox, my potential energy for oxidation has to be positive 0.76. So is that reaction favorable? Well, this gives us negative 1.95, I believe. Yes, 1.95. So that is a negative value. So that is not a spontaneous reaction. So we actually are not even going to complete this. We're going to write no reaction. So the idea here is that the sodium ions are they do not want electrons, right? Sodium has only a single electron in its s orbital. It doesn't want any more electrons. It's happy. It's got a full valence shell it's got a full shell now that its valence electron has been lost. It doesn't really want that electron. The only way we could maybe get sodium to reduce is if we provided it with a better source of electrons. Perhaps if you combined it with fluorine. So for example, if you had fluorine minus and you combine that with sodium plus, I believe that's what we want to do, then we can think that here we have a negative 2.71, and over here we have, that's actually not going to work at all, is it? That'll be negative 2.87. That's even worse. So yeah, so that's definitely not going to work. What am I thinking? That's the worst option. So that's actually never going to be stable. This is one of the reasons why the sodium-fluorine bond in sodium fluoride would be considered so strong, is that essentially these electrons are not shared at all. The attraction is highly ionic, and it's a very, very strongly ionic bond. There's no way those electrons are transferring. What would we need? We need to mix sodium with a better metal. So we'd actually need to mix sodium with something like calcium that wants to get rid of its electrons more. So let's put a calcium metal in, and here we can see that calcium at a positive 2.76. Now we're talking about a reaction, a really tiny reaction, but it would work. We could get a 0.05 volts. So that means that if you mix some pure calcium metal, you might be able to get a very tiny amount of sodium metal out of that. And so if you want to really think about this a little bit more carefully, we can probably make a guess that that in terms of buying something for your shelf, it's likely that calcium metal is a little cheaper to buy because there's a little bit less energy involved in extracting it, maybe. Or maybe sodium metal is a little bit cheaper to buy, I should say, because calcium can be used to reduce the sodium. Okay, I think I got distracted there, but let's see. Should we do one more? Let's do one last one. So I'm just going to do the last one here, this iron 2+. So here's iron 2+, and the iron, that's the one that's being reduced. We just identify the positive one. So this positive one being reduced has got a negative 0.44. Okay, so I gotta hope that aluminum is pretty strong, right? Because I'm starting from a negative position, so I'm gonna go find my aluminum. Aluminum's right here, and the aluminum is the metal, and it is usually, if it was aluminum 3+, we would say it's negative, but it's not. It's aluminum metal. It's gonna, so we need the oxidation. This is our reduction potential. We need the oxidation potential. Normally it's 1.66 negative, so the oxidation is going to be positive 1.66. Combine those. Do we get a positive number? Sure do. 1.22 voltage. So that is going to carry through. Let's just do some balancing here. We need 2 electrons for iron from the aluminum. The aluminum gives out 3 electrons at a time. So if we do 2 and 3, and then we'll get 3 irons and 2 aluminum 3 pluses. I didn't double check these other ones. Oh yeah, they're all good. Okay, so that's that. Identify the positive ion in your pair. Identify its reduction potential. Then go and look for the oxidation potential of its partner. If the 2 numbers add up to be a positive number, then it is spontaneous. If they add up and it is a negative number, it is not spontaneous. There will be no reaction. You're really dealing with the product of this reaction, of a reaction that already happened. Okay, good luck.